So, we were discussing in the last class about the stress state and the forces involved in case of rolling. So, in this class we will start with the estimation of rolling load and torque in case of hot rolling. Starting with the slip line field analysis. So, Ford and Alexander developed equations using slip line field analysis for rolling load and torque in hot rolling, rolling load and torque estimation in case of hot rolling. So, the rolling load can be expressed in case of hot rolling based on this expression, that is P is equal to K B L P into pi by 2 plus L P by H 0 plus H f. So, K here is the mean flow stress in pure shear, that is sigma 0 by root 3. And LP is the contact length between the rolls and the material, the workpiece which is undergoing rolling, and the torque is capital MT. So, so this is torque can be expressed as MT is equal to KB LP square into 1.60 plus 0.91 into LP by H0 plus HF. So, these expressions are empirical relationships which are mostly which holds good mostly for most of the, mostly for different workpiece material. So, then comparison with forgings. So, Denton and Crane noted that with a slight modification, the equation for rolling load resembles the force equation for forging a slab between rough platens. So, in case of hot rolling, the simplified expression looks like P is equal to KB LP into 1.31 plus 0.53 into multiplied by LP by H0 HF to the power half. So, this is the expression relevant to hot rolling, and then in case of hot forging, the load can be estimated from this expression, that is P is equal to KBW into 1.5 plus 0.5 into B by N. So, where H0 HF to the power half is the geometric mean thickness of the strip. So, these mathematical expressions are relevant to hot rolling and hot forging processes, and so these are empirical relationships which holds good for different materials. Okay. So, rolling load analysis. So, Sims developed a widely used analysis for calculating the rolling load in hot rolling. So, which uses a simplified form of the Oro-1 equation with mathematical simplifications. So, the rolling load equation is P is equal to sigma 0 prime B into R into H 0, that is the initial height of the workpiece, minus H f the final height of the workpiece to the power half into Q p. So, where sigma 0 prime is the flow stress in the material, B is the width of the material being rolled, R is the radius of the rolls, H 0 and H f are the initial and final thicknesses, where QP, capital QP is the complex function dependent on reduction in thickness and the ratio R by HF. Okay. So, the complex function QP varies with material's thickness reduction and roll geometry, and the expression for QP can be expressed here as square root of H 0 by 4 delta H into pi tan inverse square root of delta H by H f minus square root of R by H f ln H n square by H 0 into H f minus pi by 4. So, this is the expression, mathematical expression for QP, and so the importance of Sims analysis. So, it provides a practical and accurate approach for predicting rolling load, and it also helps optimize rolling process by understanding effects of thickness reduction and roll radius. Okay. So, these are some the variation of QP with thickness reduction. So, as you can see, so that as we have defined that this is the complex function dependent with material's thickness reduction. So, this function QP increases with the increasing thickness reduction happening in the workpiece material. Okay. So, so the QP is a complex function related to the reduction in thickness and the ratio R by HF during hot rolling. So, it influences the rolling load in Sims equation. So, the graph can be interpreted as which shows the values of QP as a function of percentage reduction in thickness. QP values increase with higher reductions and larger R by HF ratios. So, you can see that QP is increasing also with increasing thickness reduction of the workpiece. It is also increasing with the increasing R by HF, that means R is the length of arc of contact divided by the final height of the workpiece. So, that means with with all both the variables, the value of QP is increasing. So, so it indicates higher reduction or larger roll radius to final thickness ratio results in the higher rolling load. Okay. So, so this is the variation of QP with respect to the percentage reduction and also with respect to the R by HF. So, effect of R by HF ratio. So, higher R by HF values, that means higher ratio between the roll diameter and the final height of the workpiece values lead to more significant increases in QP. It suggests that rolls with larger diameter relative to final thickness have more influence on rolling load. So, understanding the QP reduction relationship helps optimizing the rolling process, and it also aids in predicting the required rolling force for given reductions and roll geometry. Okay. So, this is how we can get it to the QP. So, determination of torque in hot rolling. So, neutral angle delta and effective momentum. So, delta represents the ratio of the effective momentum A to the projected contact length LP. So, and the formula is delta is equal to A by LP. So, LP is the contact length, projected contact length, and effective moment arm is distance is A. So, that means A by LP is equal to A by R into H0 minus HF, that means diameter of the roll multiplied by the initial minus final height of the workpiece as a whole to the power half. So, so then here so this is how we can estimate the neutral angle value in case of hot rolling, and the typical values in case of hot rolling and also in case of cold rolling. So, the typical values of the neutral angle in case of hot rolling is equivalent to 0.5 higher effective moment arm due to higher temperature, and in case of cold rolling it goes up to 0.45. So, here the value of the neutral angle is lower due to increased material resistance. So, torque calculation. So, torque MT measures the rotational force needed during rolling. So, the formula of the torque MT is equal to 2 PA, where P is the rolling load, A is the effective moment arm distance. So, so here we are again multiplying this product of the rolling load and the distance of the effective moment arm is by 2, because we are talking about involvement of 2 work rolls. So, that is the reason that we are multiplying it by 2 to calculate the torque value, that is MT. So, significance. So, significance is understanding torque helps in determining power requirements of the rolling mill. So, it also aids in designing and optimizing rolling equipment for efficiency. And the practical implications, what are the practical implications? Accurate calculation of delta, the neutral angle, and this rolling torque, the MT, ensures the optimal rolling conditions, and it also helps in adjusting parameters like speed, temperature and roll diameter for desired material properties. Okay. So, so then work done in case of rolling. So, the rolling load P moves along the circumference 2 pi A, because here so this is the distance of the moment arm, that is A. So, that is why total work done is equal to 2 pi A into P, the rolling load, which is multiplied by 2. So, that is why, so it is basically the expression becomes like 4 pi A P, 4 pi A P. Okay. Where, so here so the where out of which torque MT is equal to P into A. So, the power in rolling, so power is the rate of doing work needed to operate the rolls. So, formula for power at n revolutions per second, W is equal to 4 pi A P into n. So, because we are talking about n revolutions per second, so that is why this is how we can estimate the power, that is W. So, the interpretation and practical implications. So, power required is proportional to capital P, the rolling load, and the distance of the moment arm, that is small a, and also the revolutions per second, that is n. So, critical so this is critical for designing efficient rolling mills for practical purposes to develop the parts with required thickness reduction. So, the interpretation, the power required is directly proportional to the rolling load P, the effective momentum distance A, and the rotational speed in. So, the understanding the work and power involved in rolling is crucial for designing efficient rolling mills and ensuring adequate energy supply for the process. What are the practical implications? Practical implications are knowing the power required helps in selecting appropriate motors and drive systems necessary for rolling mills. It also helps in optimizing the rolling process to minimize energy consumption while maintaining the desired deformation of the material. So, and then we are done with rolling. So, we will move on to the extrusion process, which is also another key metal forming process. So, here in case of extrusion, a process where a block of metal called a billet is forced through a die orifice under high pressure to reduce its cross section. So, shapes produced typically used for cylindrical bars or hollow tubes, but can also produce irregular shapes from easily extrudable metals like aluminum. So, these are the different kind of shapes can be produced, and the extrusion conditions. So, hot extrusion, most metals are extruded while hot to reduce deformation resistance and enable easier plastic flow of metal. So, this is necessary due to the high forces required for extrusion. So, this is the case of hot extrusion, and then so the compressive stresses. So, high compressive stresses are generated due to the interaction between the billet, the container and also the die. So, which helps prevent cracking, especially in hard to form metals. So, these are the conditions exist in case of extrusion. So, the materials suited for extrusions are difficult metals such as stainless steel, nickel based alloys, and high temperature materials are often extruded, as the process helps in reducing cracking during primary breakdown from ingots. So, because here the compressive stresses are mostly responsible for reduction in dimensions of the initial ingot. So, the high compressive stresses generated, so that it helps in preventing cracking. So, hence it can be utilized for several high temperature materials with effectiveness and with the required required alteration in the geometry. Mostly extrusion can be utilized to generate the preforms for further machining to develop the desired product dimensions. It can also be utilized to get the desired product dimensions directly from the ingot, directly from the ingot. So, both the cases are possible. So, there are two kinds of extrusion, that is direct extrusion or forward extrusion, and indirect extrusion, that is backward extrusion. So, first let us talk about the direct extrusion process. So, in this case the setup involves placing the metal billet in a container and driving it through the die using a ram. So, this is a case of direct extrusion. So, you can see the extruded metal is going out or it is exiting the die cavity in the direction of the movement of the ram. So, this is the die and this is the extruded rod that is coming out of it due to forward extrusion, and the dummy block, a dummy block or pressure plate is placed at the end of the ram to ensure even pressure and effective extrusion. And then the advantages are effective, but involves significant friction between the billet and container walls. So, leading to high power requirements. And then here comes the indirect extrusion process, which is shown here schematically. So, it is interesting to note that. So, here in case of indirect extrusion, the direction of the ram movement and the direction of the extruded billet movement, in the direction where the extruded billet is coming out, it is in the opposite direction to the movement of the ram. So, that is why we call it as indirect extrusion. So, so in this case a hollow ram is basically employed to so it carries the die and the billet remains stationary while the container is moved. So this reduces the friction forces because there is no relative motion between the billet and the container walls. So so that's why in this case the friction is lesser, and here it is the the movement here, like in case of direct extrusion the die is stationary, however in case of indirect extrusion the die is mobile. So that is a major difference between direct and indirect extrusion processes. So the power requirement, lower power is required compared to direct extrusion due to reduced friction in case of indirect extrusion process. What are the limitations? So the limitations are the use of a hollow ram limits the load bearing capacity, which imposes practical restrictions on indirect extrusion. So this is so here the use of the hollow ram is a challenge. So it limits the load bearing capacity. So so this is the concern in case of indirect extrusion. So then the case of tube extrusion. So tube extrusion, so mandrel usage. So tubes are produced by attaching a mandrel to the end of the ram. So the gap between the mandrel and the die wall determines the tube's wall thickness. So so basically this is a case which can be shown from the schematic, which can be shown later also. So this is so the so here you can see the mandrel is basically a rod which is attached with the piercing die. So then so this is the basic, you can assume that this is the thickness, and this is the piercing ram. So this is the die, and so this is the ram, and out of from the ram the piercing mandrel is basically attached, and then this is the workpiece material. So that is what is shown over here. So the workpiece material is basically initially pierced, and then it is basically the ram which is force pressing due to the extrusion force, and then the so the thickness of the hollow tube that can be obtained in case of tube extrusion is the region between the ram and the die. So this is the die and this is the ram. So in between, so this the gap between the die wall and the ram outer diameter determines the thickness of the tubing, hollow tube which is being extruded. So this is how we can arrive at its dimensions. So historical applications. So the lead pipe production. So extrusion was initially developed to produce lead pipes and later adapted for lead sheathing on electrical cables. So impact extrusion process is impact extrusion is used to produce short hollow shapes like toothpastes tubes by a high speed mechanical press. And cold extrusion usually performed cold, but considerable heat is generated due to the high speed deformation. So that is the case of cold extrusion, and the metals used are restricted to softer metals such as lead, tin, aluminum and copper. Okay. So basically, so this is the impact extrusion because of significantly higher force involved in this case. So then it can increase even higher if the material is also hard. So deforming it by impact extrusion becomes even difficult. So that is why it is generally limited to softer materials like these lead, tin and aluminum. So the tooling in extrusion. So the tooling requirements are, tooling in extrusion faces extreme stress, thermal shock and oxidation, and must be designed to withstand these conditions. So so the tool so that is why the die used in extrusion must be made of tool or die steel. So that it can withstand the extreme stress, thermal shock, oxidation, etc. Tooling assembly. A typical extrusion tooling assembly includes components like a die holder, bolster and die head, all designed for easy replacement and reworking to handle wear and damage. And die stack. So the die stack consists of number 1, that is wedge, and 2, that is die head. So this is wedge, this is die head, and 3 is the container, and 4 is the liner. So here and then others are die holder, die itself which is shown here. So which is marked as number 6, and the ball star. So, the extrusion die materials, tool steel dies. So, the die is made from highly alloyed tool steel to resist wear and withstand high stresses during extrusion. Maintenance. So, the extrusion assembly is designed for easy maintenance, allowing damaged parts to be replaced by or reworked for reuse. So, okay. So, the type of extrusion, as I have discussed already, that they can be classified as direct and indirect extrusion. So, the direct extrusion, so the metal the metal billet is pushed through a stationary die by a moving ram, causing significant friction between the billet and the container wall. So, this friction increases the required force, whereas in case of indirect extrusion, the die is attached to a hollow ram which moves towards a stationary billet. So, this setup reduces friction because there is no relative motion between the billet and the die and the container wall. So, thus requiring lesser force compared to the direct extrusion. So, so the power requirement was also lesser in case of indirect extrusion compared to that of direct extrusion. Okay. So, influence on force. So, the indirect extrusion generally requires lesser force than direct extrusion due to reduced frictional forces. So, extrusion ratio. So, the definition, the extrusion ratio is the ratio of the cross sectional area of the billet before extrusion to the cross sectional area of the billet after extrusion. So, then so the if the initial area can be defined as A initial and the cross sectional area of the extruded part can be defined as A final. So, these are the two. So, the influence on force, a higher extrusion ratio, that is greater reduction in cross sectional area, requires more force. As the billet is reduced to a smaller size, more force is needed to push the material through the die. Okay. So, this is also the concept that is also being utilized for flash in case of closed die forging, as we have discussed earlier. So, which also facilitates complete filling of the die cavity in case of forging processes. So, what is the effect of extrusion ratio? So, the larger the extrusion ratios results in higher extrusion pressures and greater deformation forces. So, so this is the effect. And then so in terms of the working temperature, so hot extrusion, most metals are extruded at elevated temperatures, which lowers their yield strength and deformation resistance, making them easier to extrude, whereas in case of cold extrusion are generally performed at room temperature and typically requires more force because the metal is less ductile and has higher deformation resistance. Okay. So, the influence on force, higher working temperatures generally reduce the force required for extrusion by lowering the material's resistance to deformation. However, material specific properties and temperature limitations need to be considered before analyzing the influence on force. Okay. So, the speed of deformation, ram speed, the speed at which the ram presses the billet through the die impacts the extrusion force. So, the ram speed, this is the case of ram speed, and then the strain rate sensitivity. So, some materials exhibit strain rate sensitivity where higher deformation speeds increase the material's flow stress, resulting in higher extrusion forces. So, this is the case of strain rate sensitivity. And then influence on force. So, increasing the speed of deformation can increase the extrusion force significantly, especially for strain rate sensitive materials. So, slow extrusion may result in lower force requirement, but longer processing times, and where the processing time, to decrease the processing time, where we increase the speed of extrusion. So, that will significantly cause requirement of higher extrusion forces. Okay. So, so the fractional reduction in area. So this is the formulation that we have discussed earlier also. So, R is nothing but reduction ratio. So, that is A0 minus AF by A0. So, that is A0 is the initial area, AF is the final area, which becomes equal to 1 minus AF by A0. So, that is what is R, that is shown here. so the extrusion ratio formula, so the extrusion ratio should not be confused with the fractional reduction in area, which is defined by small area, whereas extrusion ratio is defined as capital R, which is the ratio of the initial area divided by the final area. So that means if I need to express the extrusion ratio capital R in terms of the fractional reduction in area, that is small r, so then we can get it from here. So AF by A0 is equal to 1 minus r. So hence A0 by AF is equal to 1 by 1 minus r. Okay. So that means here, so then capital R is equal to 1 by 1 minus r. So the extrusion ratio R is equal to 1 by 1 minus the fractional reduction in area small r. Okay. So the interpretation, so for large deformations the extrusion ratio capital R is a more descriptive and practical parameter. So, so this is a typical example. So, a change in fractional reduction from 0.95 to 0.98 seems minor, but it corresponds to a substantial increase in the area ratio. So, so capital R is equal to 20:1 for r small r, so fractional reduction in area as 0.95, and capital R is equal to 50:1 for small r is equal to 0.98. So, okay, so this is how the relationship between the fractional reduction in area smaller and the extrusion ratio capital R holds good. So this shows how small changes in fractional reduction result in significant differences in the area ratio and consequently the extrusion process. Okay. So the extrusion pressure and force. So the relationship, so the extrusion pressure is directly related to the natural logarithm of the extrusion ratio. So that is P is equal to K A0 ln A0 by AF, where P is the extrusion pressure and then K is the extrusion constant, an overall factor that accounts for flow stress, friction and inhomogeneous deformation, and A0 is the initial cross sectional area of the billet and AF is the final cross sectional area of the extruded billet or the extruded part. So this is how we can calculate the extrusion pressure based on these mathematical formulae. So the natural logarithm dependence, so the logarithmic relationship highlights that the extrusion pressure increases non-linearly with an increase in the extrusion ratio. Okay. So, so here extrusion ratio is, as we have discussed earlier, R is equal to A0 by AF. So that means extrusion pressure can also be defined in terms of extrusion ratio as K A0 ln R. Okay. So here this logarithm of the extrusion ratio R depicts that it's non-linear increase with increasing extrusion ratio. So this is how it can be explained. And then the extrusion constant small k, the definition, the extrusion constant small k is an overall factor that incorporates various variables such as flow stress of the material, and also frictional conditions at the die and the container wall, inhomogeneous deformation within the billet, and the influence. Influence is the constant K plays a critical role in determining the total force required for extrusion. So as it adjusts for these secondary effects that complicate the extrusion process. Okay. So, so with this we are stopping here for this class, and in the next class we will be discussing about the different kinds of deformation involved in case of extrusion process. So till then, thank you.